Hi, today we present Deep RL Bootcamp Lecture 2. Our team members are Junyoung Kim and Sungwon Lee and Minjung Chu and Pam Xuan Chung. Our topic is sample-based approximations and fitted learning. Contents are following: introduction with recap of previous lecture, and next one is sampling based approximation in Q-learning and policy iteration, which provide the supplements of limitations in Q-learning and policy iteration. Also, beyond the other limitation, we present function fitting in Q-learning, Q and V learning. Also, the last one is an experiment in lecture. A simple robot with one arm which consists of two parts, forearm and wrist. Recap of previous lectures are following. One is optimal control. Process is considered as Markov decision process, which is MDP. S is state space and A is action space. P is called transition function, which is probability of choosing the next state when a current state and an action are given. R is reward. Gamma is discount factor, which is between 0 and 1. H is horizon. H can be finite or infinite. Our ultimate goal is finding the optimal policy pi star. It gives maximum of expected sum of rewards. When states are given, it recommends the next action which gives maximum reward in whole process. We can find optimal policy pi star with exact methods that called value iteration and policy iteration. Above one is iterate from the zero value of values in, called V, iterate to the optimal value of V, and other one is to the policy, iterate policy and find the optimal policy to maximize expectation of rewards. So it processes or has some limitations. We only have access to the underlying dynamics of the environment. And there's another underlying assumption, which is that the total number of states and actions cannot be too large because we store whole Q values or entire policies in a one table. Sample-based approximations and QV function fitting solves those of limitations. In Q-value iteration, we define ultimate Q-value, which is expected utility, which is discounted sum of rewards. We start from state S, current state S, and take action A, and thereafter we will act ultimately according to some optimal policy. So optimal Q value satisfies Bellman equation, this one, and this value can be we can get this value from the Q value iteration, like this one. It is an iterative method with this formula, and this will be the converges to the Q star. So tabular Q learning is from the limitation to solve the first limitation. The top of slide shows the usual access in the dynamics. This one. And we are enumerating over our future states whichever from the current state S. Also, we computing the exact probability of reaching the future state from current state with action A. So it is very luxurious. Instead of it, we look for much weaker form. Instead of trying to enumerate and also to compute the exact probability, we are going to do is only to require ability to sample from this transition function. Sample from the transition function. So we write this expectation form. We write this form to the expectation form, and next step is replacing the expectation to the samples. The method is called tabular Q learning. First, sampling the a future state S prime from the transition function. We look at the current estimate QKSA, which is K step of in K step Q value of in K step. So also we consider new sample estimate which consists of two parts. It is called target S prime. One is immediate reward when transition to the S from the S and to S prime, the next state, and plus discounted version of the future value according to our current estimates, and take the maximum of this one, and summation of two terms are consist of target S prime, and this 1 minus alpha qk plus alpha target S prime is become the next k plus 1 q value of S and A. So we look up the q-value iteration and sampling based approximation form of q-value iteration. So the pseudocode of q-value tabular q-learning is following. We start with some initial estimates of QSA. It might be set to 0, and we also get initial state S and action A, and we will have okay, for R, S, and A, we have initial Q values and get initial state S. For the very long loop, we sample on action A, and it is from random randomly chosen from the any probability, maybe uniform probability, and get next state from the action and current state. So it is called it is S prime. So the next step is if S is terminal, then target term is just the current reward and sample new initial state as prime. Or otherwise, we if S prime is not the terminal, target is sum of current reward and discounted form of QK and maximize it. So this one is updated to the next Q value. Also, current state S is updated by the S prime, the next state. So there's some problems in sampling of actions. So there are two ways to change. Uh, there are two ways to choose actions. First one is random action, and second one is greedy action, which choose action that maximize current Q. If we explore means choose random actions, only like random actions, we cannot run the RL agents. And if we exploit only, it means greedy action, we cannot get information of new word of the new word. So we use epsilon greedy method with if it is choose action with probability epsilon and greedy action choose greedy action with probability of 1 minus epsilon. Epsilon will be smaller when time goes by, step goes by. So here's the result of tabular Q running. Q running converges to the optimal policy even if we are acting suboptimally. It means that if we take the greedy policy, if convergence Q values. So also, even if we choose action very randomly, it also converges to optimal policy. Also, there are some caveats, which are some conditions need to hold. First, we have to explore enough. It means we have to set the epsilon large initial step. Another condition is that we have to eventually make the learning rate alpha in target and summation of target and Q will be small enough, but not decrease it too quickly. So these caveats are followed to the technical requirements that our states and actions are visited infinitely often. From the first caveat, the explore enough because if you don't visit all the states, uh, you cannot get the global optimum. So and the learning rate schedule it means alpha t such that for all states and action pairs is not the. It's followings. The conditions are followings. The first one is summation of alpha t is infinite, and the summation of alpha squared t is not the infinite. Is not uh, larger than it is smaller than infinite. In these two technical requirements, we can satisfy habits, so the Q learning goes well. Next one is followed by Junior Kim.
For Q-value iteration, we have studied tabular Q-running. From now on, we are going to apply sampling-based approximation on value iteration and policy iteration. For value iteration, we can again change the summation over stage into expectation over stage as we did for Q-value iteration. But it turns out that there is a difficulty here. Instead of having expectation at the outermost level, as in Q-learning, we have maximum over actions we can take. In general, we cannot change this maximum with the expectation, so it is unclear how we can draw the samples through this maximum function. So we cross out the value iteration for sampling-based approximation. Next, we look into policy iteration. In policy iteration, there are two steps. The first step is the policy evaluation. In policy evaluation, we iterate through this equation until convergence. Since the outermost level is expectation, we can change this. We can use the same strategy to draw samples from this transition function as we did in Q-learning. So instead of expectation, we can sample the state. This method is called the TD learning or temporal difference learning. As in Q-learning, we can derive this formula and you can also rewrite this formula as this term. And in this equation, there is a term with alpha, which is learning rate, and there is a difference between the current estimate of value function and the new estimate. So new estimate is the immediate reward plus the discounted future value function. Since this is the difference between the current time step and the estimate of later time step, we call it temporal difference learning, and this difference is called TD error. The second step of policy iteration is policy improvement. In policy improvement, we have the similar issue that we saw in previous slide in value iteration. Since we have the argmax operation here, we argmax over all possible actions, it is unclear how to draw sample through this argmax function for now, but in later lectures, we will cover how we can work around this issue. So for sampling-based approximation, we have covered Q-value iteration, which makes tabular Q-running, and the policy iteration, which we have studied about tabular TD learning. The second issue, the central problem of Q-running is that we always use a table of all Q values. This requires the state to exactly match what we have seen during training. But in real-life situations, we cannot possibly learn about every single state. there are too many states to visit them all in training, and there are too many states to hold the Q table in memory. So instead, what we want to do is to deal with this problem by generalization. We want to learn about some small number of training states from experience and generalize this experience to new but similar situations. For generalization, we study approximate Q-learning. Instead of using table of Q values, we represent Q function as a parameterized version, which we call Q theta as A. So instead of performing table lookup, we will compute this Q function when given the state and action as input, and that'll be our current estimated Q value. This parameterized Q function can be very a very simple form, such as linear functions, among some of the features that we can define by hand. So f0 through fn is our hand-designed feature, and this d theta, f theta through f theta, theta 0 through theta n is the learnable parameter for Q parameterized Q function. Or we can use complicated neural network for Q theta. For the learning rule of approximate Q learning, we use the same definition of target as we did in tabular Q learning. The immediate reward plus gamma discounted maximum Q value. But here, we instead of Q table lookup, we use the parameterized Q function. After we have obtained the target value, we perform a gradient update over theta with respect to squared loss between currently estimated Q value and the target value. We evaluate this gradient at the current theta value. In fact, the tabular Q-learning is one kind of approximate Q-learning. Suppose that theta is matrix of size cardinality of state times cardinality of actions. And the Q function, Q theta, is just table lookup into theta SA. Considering the above gradient, we replace this Q theta, Q function, with our definition, theta SA. If we evaluate the gradient with respect to parameter value at this state and action, we just get the difference between the theta value and the target value. And then if we plug this result, into the gradient update, we get tabular Q-learning update formula. This is the same formula, this one and this one. Finally, we have experimented this crawler robot example. First, we tried some completely random actions to see how the robot moves and familiarize ourselves with gym environment interface. And then we implemented the tabular Q-learning algorithm with epsilon grid exploration to find optimal policy. And this is the result. This is the result of random action, and this is the result of learned crawler robot. After the learning is successful, we can visualize the learned robot crawler. Remember, we learned this robot just from interacting with the environment instead of kicking into the dynamic model. Thank you for listening.